Okay, hello everyone, and we will continue with Subhash's fourth lecture on unique games conjecture. So, Subhash, please.
Oh, okay. So all right. So I want to spend like maybe 10 minutes just completing the proof that we started, which is the soundness analysis of the PCP to show the hardness result for max cut. So just to quickly recall what we did last time, we defined the unique games problem and the unique games conjecture. So unique games problem is just the label cover says that the label set on both sides is the same. Let's say set of integers from 1 through little n, and then all these projection maps from vertices W to the vertices V, they are just identity permutations or one-to-one maps or bijections. And then the conjecture is that such instances of unique games or label cover, for these, it's NP hard to distinguish whether there is a labeling which satisfies almost all the edges versus no labeling satisfies more than some tiny delta fraction of the edges. Now, the PCP for max cut is now constructed by taking this hard instance of unique games problem and then asking the prover or the adversary to write down the long code encodings of the labels. So now the prover or the adversary for every vertex, let's say V or W, writes down a Boolean function, right, on n bits, n being the number of labels. So these call these functions f sub V's and f sub W's on either side. And right, and then the PCP itself carries out this test. F of x is not equal to f of y, which is this 2-bit noise test or dictatorship test, where x is input and y is the noisy version of x. And as I said the last time, actually what you need to do is, in fact, keep the left-hand side completely virtual and carry out the test only on the right-hand side. So we really will have only long quotes f sub w's for the vertices w only on the right-hand side. And then the test itself will pick one vertex v at random from left side, two of its neighbors w and w prime, and carry out the test f of x is not equal to f of y on the quotes for w and w prime. So that would be the test. Okay. So here I'm just saying the same thing in words, right? And now we want to analyze the test. And just to emphasize, these x and y are a correlated pair of inputs, where the correlation rho is negative. It's sort of close to -1. Right. And now we want to do the soundness analysis. Well, firstly, the completeness property is sort of easy to show that in this, if the label cover instance had a labeling which satisfied almost all the edges, then this test overall will accept with probability essentially 1 minus rho over 2. So that's evident. So the soundness, we want to show that if the test accepts with probability marginally more than 1 over pi cos inverse of rho, then we can actually, from these given supposed encodings, right? From these Boolean functions, we can actually come up with a labeling which satisfies a good fraction of the edges of the label cover or unique game, and that would be a contradiction because we are in the soundness case. And naturally, what you would want to do is to extract these labels. The labels are simply these coordinates, right, from 1 through n. So you simply, as decoding, take all the coordinates whose influence is large. Okay, and then of course you have to worry about some technical issues, and it generally becomes messy or ugly. But there is a rather clean way of doing it.
Sorry, Subhash, there is a question in the chat.
Right.
That is perhaps not clear how this relates to the max cut problem. So.
Oh, right. So yeah. So so somehow, you know, somehow I have this tendency to take these things for granted. So this is why I said right in the first lecture that you should really internalize this view of hardness of approximation and building a PCP and talking in terms of tests and verifiers. Okay. So what we did was the following, right? So this is the PCP, right? As a PCP, you simply have these Boolean functions, right? And you are carrying out a test. You look at two functions, f sub w and f sub w prime, and make the test whether this f of x, fw of x here is not equal to f sub w prime at y. Okay. Now this is the PCP viewpoint, but now you can think of it as actually constructing a graph where it's a Boolean function, right? So it's a function on plus minus 1 to the n. So this entire string or word is really thought of as a hypercube, n-dimensional hypercube, right? So and then the function itself will be a cut in the hypercube. Okay. But simply as a graph, these are just hypercubes. And then whenever you decided to make a test that f of x is different from f of y, but of course x from this code and y from this code, then that amounts to actually constructing an edge going from the point x in this hypercube to the point y in this hypercube. And that gives you a graph. Okay. And then, so this is the max cut instance. And now you want to analyze cuts in this max cut instance. Okay, which is same as, but the cuts in this instance are simply plus minus 1 labelings to the vertices, which then simply amount to the Boolean functions, right? And then the size of the cut will be precisely equal to acceptance probability of the test. So does that answer the question? Yeah, so I hope it does. Right, so yeah, so I'm going back and forth between the PCP view and the hardness view in terms of the actual graph. And this is what I insisted in the first lecture, that you should just become comfortable switching back and forth. All right. Yeah, so right, so I'm talking now purely in the language of PCPs, tests, and acceptance probabilities of the tests. But really what I'm doing is analyzing the size of the cut. Okay. And this was just a kind of neat way of doing this. So let's look at the probability that the test accepts. So the test accepts it. This expression evaluates to 1, right? If these two bits that I read from the proof, they turn out to be not equal, and then you get 1. If they're equal, you get a 0. So the test acceptance probability is simply the expectation of this expression over all the choices that you made during the test. You first chose the vertex v from the left-hand side, picked 2 of his neighbors w and w prime, then you pick these locations x and y, and right. Yeah, and then you can go through this expression line by line, which we did last time. And then the point is, this turns out to be simply expected value over v, which is the choice of the left vertex, 1 minus the stability of the function f sub v, where f sub v is a function that we defined for the sake of analysis, right? The prover or the adversary only gave the functions f sub w's, right, on the right hand side. And now, just for the sake of analysis, we define a function f sub v to be the average of the functions f sub w's over all w's which are neighbors of v, neighbors in the unique games graph, okay, or the label cover graph. And the functions f sub w's are Boolean, plus minus 1 valued, but we are now taking their average. So the f sub v will become real valued, but still bounded in the interval -1, 1. Okay, so to summarize, the overall acceptance probability is simply expected value over v, 1 minus the stability of the function f sub v. And now if the overall acceptance probability exceeded 1 over pi cos inverse rho, so if it's that plus epsilon, then by the standard averaging argument, it must happen that for at least epsilon over 2 fraction of the vertices v, right, after choosing the vertex v, and you can call such vertices good and just fix such a good vertex, right? Then the 1 minus the stability is at least this threshold 1 over pi cos inverse rho plus epsilon over 2, right? Because this expectation will exceed this threshold. So with at least some slight probability over the choice of V, whatever is inside should exceed the threshold. Okay, so I'm saying something very simple here. Yeah, but now we use this theorem, the theorem number 3, that majority is the unstablest function, right, under the negative row. So if you have a function whose unstability exceeds that of majority, so this 1 over pi cos inverse rho is the instability of the majority function. If so, then the function must have an influential coordinate. Okay, so there must be a coordinate I sub 0 whose influence is at least delta, and in fact the degree k influence is at least delta, where delta and k, they have some dependence that depends on this epsilon and rho, and the precise dependence doesn't really matter, so let's just skip that. Okay, so but the conclusion is that the function f sub v must have an influential coordinate. Okay, and now we somehow from this we want to do the decoding, but note that this function f sub v, this is in some sense it's a virtual function. We just constructed it for our own sake of analysis. Okay, but to actually find the labeling, right, all that these vertices w's and w primes have access to are these functions f sub w's and f sub w primes, right? You only can decode using these functions, but the function f sub v that we constructed, right, this is just for our own sake. But then it stands to reason that if f sub v has influential coordinate I sub 0, and f sub v just average of the function f sub w's, right? This is what I defined here. F sub v is the average of f sub w's. And then if this guy on the left-hand side has influential coordinate, it stands to reason that the f sub w's should also have, typically speaking, influential coordinate. And the same coordinate should be influential. And that turns out to be the case. And there is a neat proof. So let me go through this proof. Again, I mean, I'm not saying anything deep here. It's just to illustrate that it's another trick of the trade, right? And it's good to know tricks of the trade. It makes the life easier. Yeah, so what we said is this in coordinate I sub 0 has influence at least delta, degree k influence on the function f sub v. Okay, now we do some manipulations. Now, by definition, this influence is simply sum of squares of Fourier coefficients over sets which contain that coordinate I sub 0. And the sets are of size at most k. Now, since f sub v as a function is a average of the functions f sub w's, the same thing holds for the Fourier coefficient. The Fourier coefficient at particular set S is also the average of the Fourier coefficients of the function f sub w. And then you're taking the square by Cauchy-Schwarz with inequality in the right direction. You can pull the square inside, okay, and then pull the expectation outside. And then this is expected value of w, and what's inside is simply the influence of that I sub 0 on the function f sub w. And f sub w's are the ones that we actually have access to for the decoding, right? Right, and then since there is a lower bound of delta on this, right? And then it follows again by so-called averaging argument that for at least delta over fraction of the w's, I sub 0, the same I sub 0 has influence of at least delta over 2 on the function f sub w. Okay, therefore, many of these f sub w's which are actually present, they also have influential coordinate. Okay, and now we are ready to do the actual decoding, right? Right, and define the labeling, and that's the end of the soundness analysis. And the decoding is just straightforward, right? For every vertex w, you have access to the function f sub w. So just make a list of all coordinates I whose influence is at least, let's say, delta over 2, the degree k influence. Okay, and here is the again to emphasize why we use degree k influences, because as we emphasized last time, if you made a list of all those whose degree k influence is at least delta over 2, there aren't too many of them. There is an upper bound of, let's say, order k over delta on the size of the list. So this is the list called all the candidate labels for w, right? These are all the possible candidates, all influential coordinates. And then you are going to pick one coordinate at random from the set of all these influential coordinates. Okay, so that's what you will do for every vertex w. It's a randomized labeling. Now, of course, the label cover or the unique games instance had two sides. So you have to come up with a labeling to the vertex V on the left side as well. And then you would do something which is natural. For any V, you will pick one vertex, one neighbor, W prime, at random from the right-hand side, and then assign a label at random from the candidate labels for W prime, right? Meaning the coordinate which is influential for W prime. Okay, and this is the randomized labeling. And it's easy to now see that this is a good labeling. I mean, you might get a bit lost, but let me just quickly go through it, and you can certainly take a closer look. And now let's show that for a good fraction of edges, VW, this randomized labeling succeeds with good probability or some constant probability. Okay, and now you can do the standard kind of routine argument. So first of all, right, when you pick a random edge VW, first of all, epsilon over 2 fraction of the vertices V are good in the sense that we defined. So let's assume that the vertex V is good. Once the vertex V is good, we concluded that at least delta over 2 fraction of its neighbors, W, they do have a coordinate I sub 0, which is influential. And therefore that I sub 0 appears in the candidate list, right? And then we are going to pick that I0, hit upon that I0 after picking one at random from that list. And in fact, we will hit on that I0 for both the vertex W and a random neighbor W prime of the vertex V, right? So with probability, let's say delta over 2 times delta over 2. That's the probability that we will hit upon those specific W prime. And then with probability, which is 1 over the square of the list size, we will hit upon that particular I0 for both W and W prime, right? So with this probability, we succeed, meaning we end up giving the label I0 to the vertex V, and well, which is sort of gets inherited from label for W prime. And then we also manage to assign I0 to the vertex W. Okay, and then we succeed, meaning we satisfied the edge VW. We assigned the same, managed to assign the same label to V and W. Okay, so there is some constant probability, whatever this is, but it only depends on epsilon and deltas, and independent of the dimension n or the number of labels n, right? That's what is important. Yeah, and then we get a labeling which succeeds with constant probability or on constant fraction of edges, and this finally is a contradiction, provided we chose the unique game or label cover instance a priori whose soundness was sufficiently small. Okay, and this proves that the test overall accepts with probability at most 1 over pi cos inverse rho plus epsilon. Meaning, yeah, now if you switch back to the actually in terms of the graph that we constructed, there the size of any cut is at most 1 over pi cos inverse rho plus epsilon, and that completes the soundness analysis, and that completes the reduction to max cut. Okay, so yeah, and that's the end of this topic of max cut. Yeah, so if there is any quick question, I can answer, and then we will move to the next topic. Yeah, and of course, as I said, my goal intentionally is to go a bit fast and give you a really good solid background on this topic, so that you are actually ready to, in fact, start reading things by yourself if you are interested in. And as I said, I'm willing to accept some risk of losing some or maybe even many of you during the lecture. It's fine.
Does that cost come from the worst case contribution for an age in the max cut algorithm?
What comes from?
The cosine function.
Yeah, so this is the remarkable thing about this topic of max cut. That
the Gomez algorithm. Yeah.
So there are two sides. There is an algorithmic side and there is a hardness side. Okay. From the algorithmic side, the cosine function comes for the same reason, right? That you have pair of vectors from the semi-definite programming solution, right? If their angle is theta, then its contribution to the semi-definite SDP objective, so to speak, is 1 minus cos theta over 2. So it naturally comes from the algorithmic side in the Gomans-Williamson algorithm. And then it naturally also comes from the hardness side because we use this majority stabilis theorem. And then it's this 1 over pi cos inverse rho is precisely the instability of the majority function under correlation parameter rho. Right, and so it comes from both sides, and in fact, they exactly agree in between, right, in the middle. And therefore, you get matching hardness result and matching algorithmic result. And this is the whole, in some sense, beauty of the whole affair. Yeah, so I would highly recommend carefully going through both algorithm and the hardness reduction and seeing how they somehow match. Right.
Thank you.
Okay, all right. So let me move on to the next topic. And yeah, this, if you wish, I mean, you can think of it as, in some sense, again, as a rather self-contained lecture. And now we only have about hour and 40 minutes for this whole topic. So yeah, so only I will only be able to cover only so much. And I think for the large part, what I will cover will be essentially pure combinatorics. Okay, so I don't think I would even get to the part of the actual reduction. Okay. So in that sense, it should actually be a rather self-contained lecture, right? Nice pure combinatorics, and this part I will actually try to go slow. And as I said, in fact, whatever I will say, I already gave a lecture at Harvard a few months ago. And you were supposed to watch this lecture even before I started. So in fact, what I'm going to do is basically repeat the same thing, whatever I did that in that lecture. So I think for those who did saw the lecture, right, and that was supposed to be your homework, you should be quite comfortable with whatever I'm going to say now, and it should be a good revision for you. But even otherwise, I will go slowly. Right. Yeah. So now I will we'll see what this 2-to-2 games theorem is, and then I will describe some, at least in this case, only the combinatorial aspects of what goes into the proof of the 2-to-2 games theorem. But before we start, even defining what the 2-to-2 games theorem is, there's one thing I want to point out is in this proof, so we did with our collaborators a couple of years ago. So we did something which was remarkably different than even at the level of the combinatorics or the testing primitives that were involved. Remarkably different from the general scheme that was used in all prior works. Okay, so I want to point out what was this remarkably different thing that we did. So recall that we studied this linearity test, right, in the context of Hastad's 3-bit PCP. So we were given a function from f2 to the k to f2. F2 is just the standard, the Boolean field, and to check that it is linear, we tested whether f of x plus f of y equals f of x plus y for a randomly chosen input pair x and y. And what we proved using elementary Fourier analysis is that if the test accepts with probability which is slightly above half, say probability half plus epsilon, then actually the given function f does have a good agreement with a truly linear function g, meaning there exists a actual truly linear function g, such that the g agrees with the given function f on at least some half plus epsilon prime fraction of the inputs. Okay, so non-trivial acceptance probability of the test implies non-trivial agreement with a actual linear function. Okay, so this is what was we concluded. And in fact, the way to come up with this function g is simply to show that if the test accepts with probability half plus epsilon, then there must be a Fourier coefficient of magnitude at least epsilon prime, and that Fourier coefficient is precisely the linear function g. Okay, and in fact, you can do something more. You can even do, and this is viewed as a decoding, right? Given a function f, the function g, which is linear, is its decoding, so to speak. And in fact, you can do what is called the list decoding, meaning you can make a list of all functions g which do have agreement of half plus epsilon prime with the given function f, because in principle there could be more than one such functions. And turns out, which is easy to prove, that if you made such a list, this list will be of bounded size. In fact, you can show that the number of functions g which have half plus epsilon agreement is not more than order 1 over epsilon prime squared. Okay, and well, if I were teaching this in a class, I would ask you to give this as 5-minute quick exercise to check whether you are doing well in the course. But let me give you the answer right away here. This is simply because half plus epsilon prime agreement, it really amounts to simply having Fourier coefficient of magnitude epsilon prime. But then sum of squares of all Fourier coefficients is 1. So the number of coefficients which are at least epsilon prime cannot exceed more than order 1 over epsilon prime squared. Okay, so the point being that even if I made a list, the list is bounded. Okay, so there are two things here that you can do a decoding. Okay, you can find a code word or a truly linear function g which has a good agreement, and then you can even do a list decoding with bounded list. Okay, and these two properties, decoding and then the list size being bounded, this is very, very important, and has been necessary in all the PCP constructions so far. But this will break down in the proof of the 2-to-2 games theorem that we will see, and we do have to do something a bit different. Okay? So I just wanted to point this out a priori. So here there is an analogous example which arises in the algebraic proof of the PCP theorem in the analysis of what is called the low degree test. But since we didn't do this during this course, let me skip that. Okay, so now let's state what the 2-to-2 games theorem is. So it's a variant or a weaker version of the unique games conjecture. So let me quickly state unique games conjecture first. Well, we already stated what unique games conjecture is, but here I'm going to state it in a slightly different format. And just trust me that the version that I'm stating here is equivalent to the version that we stated before. So there will be two differences from the version that we stated before. Before we stated in terms of a bipartite graph having two sides. Here, this will be non-bipartite graph. Okay, and that's one difference. And second difference is there we allowed constraints to be arbitrary permutations or one-to-one or bijections. And here the constraints will be, in fact, very special, even further specialized ones. Okay. These will be linear equations over an additive group. Okay, so the way this conjecture is phrased here, as I said, it's a bit different than what we did before, but just trust me that is just equivalent formulation actually. So here is the conjecture that that is NP hard to tell for every given epsilon. It's NP hard to tell whether an instance of unique game has an assignment satisfies at least 1 minus epsilon fraction of the constraints, or no assignment satisfies more than epsilon fraction of the constraints. Okay, and what are the constraints? Well, firstly, what are the variables? So you have variables x1, x2 up to x sub n, and these variables can take values over a group. Okay, and the group specifically that we will use is f2 to the L dimensional right space over vector space over f2. And think of the dimension little l as a constant. Right? So it's really a additive group of constant size, of size 2 to the L. Okay, and then the constraints are simply linear equations over this group where every equation has only 2 variables. Okay, so you have n variables x1 through xn, and for some pairs xi xj there is a constraint called xi plus xj equals constant d sub ij, and of course these constants will be from this group. Okay, and right, and this is what is a unique game. And this is unique because if you think of the constraint on the pair xi xj, it's really a permutation constraint in the sense that for every value to xi, there is exactly one value to xj for which you can satisfy the constraint, and vice versa. For every value to xj, there is only one value to xi, right? That's necessary to satisfy this linear equation. So I hope it's clear that this is really a unique game. Okay, right, and that's the unique games conjecture. Now the 2-to-2 games conjecture, which is now a theorem, is the same thing. And of course, the conjecture is that for every epsilon that you want to achieve, there is a large enough constant integer L. So for every epsilon, there is a large enough sized, but still constant size group, F2 to the L, for which distinguishing between 1 minus epsilon and epsilon is hard, NP hard. Okay, and the 2-to-2 games theorem is very similar, that for every epsilon, there is a large enough integer L, which defines the size of this group. That is NP hard to distinguish whether the optimum is 1 minus epsilon versus at most epsilon, except that now the constraints are not quite unique constraints, but 2-to-2 constraints, meaning the typical constraint looks like this, that it's again on a pair of variables, and then xi plus xj, it has to take a value which is either a constant b sub ij or some other constant b sub ij prime. Okay, so, or to say in other words, for every choice to the assignment to the variable xi, there are exactly 2 assignments to xj, which can satisfy the constraint, right? And vice versa. For every assignment to xj, there are exactly 2 assignments to xi to satisfy the constraint. Okay, and then the theorem is the same, that for such a constraint system, it's hard to tell whether the optimum is 1 minus epsilon or at most epsilon. Okay, so that's the theorem. And recall, well, I mean, this is a recall with a smiley face, meaning even before the course started, I recommended that you listen to this introductory lecture, which kind of gave an overview of what the course is going to be about. So if you did that, then you would recall that this 2-to-2 game theorem has quite interesting consequences. For example, firstly, it shows that the unique games is also NP hard with a gap of half versus epsilon. The unique games conjecture would be to show that the gap of 1 minus epsilon versus epsilon is hard. Okay, but we can still get something. We can get a gap of half versus epsilon, and this is simply by if you have this 2-to-2 games theorem, you can take a very easy reduction to unique games by rewriting this constraint as 2 separate equations: xi plus xj equals bij and xi plus xj equals bij prime. Okay, and then in the yes case, instead of satisfying 1 minus epsilon of the constraints, you will now only satisfy half of them, right? Because you will get 1 out of the 2 equations right. So you get half versus epsilon is NP hard, which is already quite significant, in fact, very significant result. You can also get application to max cut. So for max cut problem, you can consider this more specialized version of max cut, where even in the yes case, the best optimal cut is only of size half plus epsilon. Okay, and then the question is, can you find cut of size half plus epsilon prime, where epsilon prime is a function of epsilon? And then turns out you can find cuts of size half plus epsilon over log 1 over epsilon, and this result is optimal, meaning there is an algorithm, and now there is also the matching NP hardness result, and that's a consequence of 2-to-2 games. You can also show that as a consequence, it's NP hard to color almost 4 colorable graphs with any constant number of colors, let's say 1,000,000 colors, and this more or less answers a rather notorious question in graph theory and combinatorics. Another interesting consequence is this is called the intermediate complexity theorem, which was actually viewed as counterintuitive or not even possible a priori. So what it says is that this unique games problem with gap of half versus epsilon, to solve it deterministically, the amount of time needed would be something which is intermediate between 2 to the n to the epsilon prime and 2 to the n to the epsilon double prime for some epsilon prime, epsilon double prime that depend on epsilon, as opposed to being truly exponential, which is of the kind 2 to the constant times n. Okay, so prior to this result, researchers had good reasons to believe that all constraint satisfaction problems, they are either easy or extremely hard. Easy meaning they can be solved in polynomial time, or extremely hard meaning their complexity is truly exponential, which is 2 to the constant times n, n being the number of variables. In fact, this is what is believed to be the true complexity of 3-SAT. This is called exponential time hypothesis. Right, but turns out that actually the unique games problem, its true complexity is something intermediate, something like, let's say, between 2 to the cube root of n and 2 to the square root of n, which is quite counterintuitive. Right, and this and many other reasons were given to argue why actually unique games conjecture is ought to be false, and this seemed to be the dominant, in fact, vastly dominant position of the researchers in theoretical computer science, that the unique games conjecture ought to be false. Before we proved this 2 to 2 games theorem recently, and now my impression is that we had a complete 180-degree switch in the popular opinion, and my impression is that now almost most people now believe that the unique games conjecture ought to be true.
So Subhash, so how important is it that on the right-hand side you always offer these 2 B's, so B and B prime? What if you offered 7 B's? Would you still get these?
It would still be a great result.
But
it will still,
would you be able to
imply
get
many of it will still imply these implications.
Mm-hmm. Okay.
But we just get 2, so
okay, yeah.
we already get the best you can hope for.
Yeah. Thanks.
Right. Okay, and here is like very high level view of how the proof goes. Well, at the end of the day, these are all just reductions, right? And in this case, it's a reduction from 3-lin, and we studied 3-lin. And the hardness result for 3-lin on the host of 3-bit PCP. So it's a reduction from that hard instance of 3-lin to the 2 to 2 games problem. But just to give analogy with the max cut, it was a reduction, but then to show that the reduction is correct, and even to actually design the reduction, we had to use theorems about Boolean function analysis, right, which was the majority stablest theorem. So something similar is true here. We do have to discover new theorems, new combinatorial or analytic theorems. And here are the theorems concern structure of, or rather expansion of sets in a specific family of graphs called the Grassmann graphs. So it turns out that we have to show a theorem about expansion in Grassmann graph. So that we will call the Grassmann expansion theorem. So I will state this during the course of this and the next lecture. Then we'll show that this implies a linearity testing theorem on the Grassmann graph. So we'll study this, and then I don't think I will have time to actually show you the reduction, but the reduction does appear in these lecture notes if you want to take a look. And also I wrote a whole big survey on this topic, 2 to 2 game proof of 2 to 2 games theorem, which is also available to you if you want to take a look. And also one thing which does appear in these lecture notes is the proving this expansion theorem in its full generality. That's actually rather difficult, but you can prove a special case of it, like a sort of toy version. And that toy version is actually also already quite illustrative. And the proof for the toy version, it does appear in these lecture notes, written lecture notes, as well as in this survey that I wrote. So if this kind of things interest you, I very much recommend taking a look, just even proving this toy version. Okay, right. So what I will be able to cover, so we have about 20 minutes now, and the next lecture is this linearity testing theorem, and then the expansion theorem, sort of making the statements and how explaining the statements, and then the proof that the expansion theorem implies the linearity testing theorem. Okay, so this is what we'll be able to do. All right. So what's this linearity testing theorem? It's sort of, at least at a high level, the goal is similar. We want to test whether a function is linear. But here, instead of the Hastad 3-bit PCP, where the function is given as such, right? The function itself is given to you, was given to you. Here, we are not going to use the function, the truth table of the function per se, but an encoding of this function in a different encoding scheme. Okay, so that will be one difference. And another difference would be that the Hastad 3-bit PCP was 3-query PCP, but here we will have to have a PCP or a test which makes only 2 queries, okay, to the encoding. And it has to be a 2-query with a specific predicate called the 2-to-2 predicate, because it will be used to prove the 2-to-2 games conjecture, right? So there has to be some connection or similarity between the final goal and the testing primitive. So we'll see what 2-to-2 predicate is. And we will have to, as I mentioned in the beginning, with this rather new remarkable feature that we will have to, we will really will not have bounded list decoding. In fact, we won't even have the standard decoding. So we'll have to somehow get around that. Okay. Okay, so to motivate what this even encoding is, and I keep using this word Grassmann because whatever objects we are going to study, these were at least defined before in the combinatorics literature, and these are called Grassmann graphs. When we view these objects as graphs, which we'll do a bit later. Okay, so what's this linearity test? So to motivate this, we have to start with the following very easy observation. So we'll be concerned about functions on the vector space F2 to the k, right? And the values are also in F2. And ideally speaking, this function functions are linear, right? The linear functions. Now here is a simple observation. If this function F is linear, then, and if L is a subspace, right? It's a vector subspace of the space F2 to the k, and its dimension is little l. So henceforth, capital L will always domain a subspace of dimension little l. Okay. So if L is a subspace, then restriction of the function f to the subspace L, okay, is also linear. Okay. All right. So this is completely self-evident, right? If all the global function is linear, then its restriction to every subspace is also linear. Now, but it's a linear on a subspace of dimension little l. And therefore, if you want to write it down, you can write it down by, because how many linear functions are there on subspace of dimension little l, right? There are exactly 2 to the l of them. So you can write it down using an alphabet of size 2 to the l, right? Good. And now I define Grassmann encoding. So the goal is to encode a function f, which is linear function, okay? Or if you want to think of it as, you can think of it as encoding a k-bit string, because every k-bit string defines a linear function, right? Which are the coefficients of that linear function. So to encode a linear function little f, we will write down for every subspace capital L of dimension little l, the restriction of the function f to that subspace L. Okay. So, just I will stop for like just few seconds, just so that you digest this definition, right? So the goal is to encode a function, linear function f, and the encoding consists of writing down for every subspace L of dimension little l, restriction of f to L, okay, and which is a symbol from an alphabet of size 2 to the L, okay. So you write down one such symbol for every subspace L. And what you write down, let's denote it as capital F of L. So this capital F will this will denote the encoding, and I will refer to this as a table. So this capital F will be referred to as a table. Okay, so the encoding of linear function little f is this table capital F, right? Now, what's the length of this encoding? The length of the encoding is number of little l dimensional subspaces of a k dimensional vector space, right? So you can calculate this number if you want, and these are sort of analogs of the binomial coefficients. Okay, these are vector analogs of binomial coefficients. Okay, so I hope this was clear. And then here is a linearity test. So you are, as always, right? The goal here is you are given a table which, ideally speaking, is the correct encoding, right? But the prover or the adversary could try to cheat and write down an arbitrary word. And your goal as a tester is to probabilistically test whether it's a correct encoding, right? So in this case, you are given this table capital F, right, which writes down this the linear function for every subspace L of dimension little l. This entry of the table, right, capital F of L. This is a linear function, and this is a linear function on that subspace. So this is what you are given, and your goal is to test that this is a correct encoding, meaning the entries in this table, they come from some global linear function, right? And these are restrictions of some global linear function. This is what you are trying to test, right? So how would you test this? Now, of course, if all these came from restrictions of some global function, then if I have pair of subspaces L and L prime which intersect, then the linear functions f of L and f of L prime, they must be consistent on the intersection, right? Yeah, and that's all. That's all the test will do. It will pick a pair of subspaces LL prime that intersect, and it's important that we actually only pick those pairs LL prime for which the intersection is maximal. Okay, so if they are L dimensional, the intersection needs to be of dimension L minus 1. So you pick a pair of subspaces LL prime which are maximally intersecting, and then check whether the linear function f of L, right, which is what the table gives you, it's consistent with the linear function f of L prime, which is also given by the table. Okay, so they agree on the intersection L intersect L prime. Okay, so this is the test. So again, I will wait for like just 10 seconds for you to digest this. What the test is, right? All right. Okay. And now we want to analyze the completeness and the soundness of this test. So first of all, the completeness. Now it's clear that if this table is encoding is a correct encoding of a global linear function, right? Then each entry of the table will be restriction of some global linear function f to these subspaces. And of course, if everything is restriction of a global space, then clearly on two subspaces LL prime which intersect, the answers which are given, which are the entries of this table, they will be consistent, right? And therefore the test accepts with probability 1. So I hope this is clear. Now, important property is that this acceptance predicate, right? So you will accept if and only if f of L and f of L prime, they are consistent on the intersection. This acceptance predicate is what is called 2 to 2, meaning for every answer or entry of the table f of L, there are exactly 2 answers to f of L prime for which you would accept, meaning for which this identity, this equality would hold. And for every answer to f of L prime, there are exactly 2 answers to f of L. Okay, and why is that? This is because the intersection has dimension L minus 1. Okay, so if you have answer f of L, meaning you are writing down a linear function on L, and therefore you are also writing down the linear function on the intersection, right? L intersect L prime, and now you move to L prime. It has only 1 extra degree of freedom, right? So there are on that extra degree of freedom, Your linear function could take only two choices, 0 or 1. So you only have two ways of extending the linear function to L prime. If you already know what the linear function is on the intersection, okay? So for every answer to L, there are only two answers for L prime, which are acceptable, and vice versa, right? And this is why this is a 2-2-2 test, okay? And this is very important, okay? Okay, so now the soundness analysis. Yeah, but as I said, this is not such a straightforward task. Now, if you are even a PCP researcher, right? You will speculate that the following conclusion holds, and this is how we started. We started with this speculation, which actually turns out to be false. But here is a natural thing you would want to be true, okay? That if the test accepted with some constant probability, let's say probability 25%, then you would like to do a decoding, right? You would like to claim that the given table F is consistent with some true encoding or a correct encoding, meaning you would like to claim that there is some global linear function such that your table is consistent with that global linear function on some constant fraction of the subspaces. Okay, I mean, if this were true, I mean, you would be in great shape, right? So here is the speculation that if the test accepts with probability at least delta, meaning on delta fraction of the pairs L prime that the test picked, the table answers given by the table F, which is F of L and F of L prime, they were consistent on the intersection. Okay, and suppose this happened for delta fraction of the pairs L prime, then is it the case that there must exist a global linear function, say call it G, on the entire space, such that the table is consistent with the global linear function on some delta prime fraction of subspaces L? Is it true? Okay, I mean, this is the question that one would naturally start with. This is how we started with. Okay, and well, if the answer was yes, I mean, it would have really simplified matters a lot. Unfortunately, or maybe fortunately, because it leads to nicer mathematics, the answer turns out to be no. Okay, and at least my goal for the next few minutes would be to give you a counter example showing that why the answer is no. Okay, so here is a counter example, meaning I will construct a table capital F such that it passes the test with constant probability, but it has no agreement whatsoever with any global linear function. Okay, that's my goal. So here is a counter example. So here is the global space F2 to the K. Pick m points x1, x2 up to x sub m in this space, and for each point, let's say point xi, in this case point x1, look at all subspaces L which contain that point x1. Okay, so for each I, let S sub I be the set of all those subspaces L which contain the point xi, right? And you expect that for different points x1, x2, x3, these sets will be nearly disjoint. So let's just assume that these sets are disjoint for the sake of simplicity. Okay, and take enough of these points x1, x2, x3, I mean, how many you need to take? There is a specific number here. So take enough of them so that these sets S1, S2, they cover constant fraction of little L dimensional subspaces. Okay, so you can certainly do this. Okay, and now what I'm going to do is for each set Si, I'm going to make an assignment to those subspaces according to a global linear function, but I will use different linear functions for different sets. Okay, so formally, this is what I do. I pick m global linear functions, but these are distinct. Okay, and then construct the following table So what this table does is, if a subspace is in the set Si, meaning for subspaces containing the point xi, I make an assignment according to the function f sub I, right? So, right, I'm supposed to assign a linear function to that subspace L. So it will be the restriction of the function f sub I to that L. Okay. And then, of course, there are some subspaces which I did not even cover. There you can just make some arbitrary or random assignment. This is a minor point. Okay, so that's my example, counterexample. So to show that it's a counterexample, first I will show that this table that I constructed has no assignment with no agreement, with no non-trivial agreement with any global linear function. Okay, and this is sort of self-evident, right? Because I partition all subspaces into I broke them down into groups or pieces, and on each group I use a completely different linear function, right? So I cannot have a single linear function which has agreement with all of them, or even some good fraction of them, right? So there is no global linear function f which agrees with my table on some delta prime fraction of the spaces L. Right? Is that clear? Right? Because I use something completely different on different pieces. Okay, so there is no single one, single global linear function which has good agreement, right? On the other hand, this table does pass my test with constant probability. Okay, and let's see why it's important. Okay, so what did the test do? Right, it picked a pair of subspaces LL prime, right, whose intersection was maximal intersection. Now, when you picked LL prime, these sets S1 through Sn, they covered constant fraction of the subspaces. So with constant probability, the L will belong to some Si, okay, which is same as saying that L will contain the point Xi. Okay, so yeah, so let's say L contains the point Xi. Now, now you picked a random neighbor of L and called it L prime, right? But what is L prime, right? So L prime is a random subspace which has intersection of L minus 1 dimensional with L. Okay. Now, if L contain the point Xi and I move to L prime, keeping the intersection with L minus 1 dimensional. Okay. So what's the probability that Xi will still be contained in L prime? Right. Right, and this has easy answer, right? Because if the intersection of L and L prime is 1 dimension less, it means that in terms of size, the size of the intersection is half of the size of L, right? And if you did this at random, Xi will still be there with probability 1/2, right? If you move from L to L prime, Xi would still be in L prime with probability 1/2. Okay, so I hope this is clear, right? And if at least one participant could just unmute himself or herself and just say yes, right, I would be very happy.
Yes, makes sense to me.
Okay, very good, right? Right, and then so Xi will still be in L prime with probability 1/2, and then once it is L prime contains Xi, the L prime was also got assigned according to the same function, because L and L prime are now both are in the same set Si, and they got both assigned according to the function f sub I, right? And therefore the answers will be consistent. Okay, right, and then the test accepts, right? So of course L belongs to some Si with probability which is a constant, and once that happened, L prime also belonged to Si again with probability 1/2, which is a constant. So altogether with constant probability, the test accepts. Okay, so the conclusion being that the test accepted with constant probability, but the given table F has no global agreement with any global linear function. Okay, so that's the counterexample. Now, yeah, so the source of trouble, why this counterexample even arose, are these sets of the type S sub x, right? That for some point x in the space, if if you take the set of those subspaces L which contain the point X, okay, this set, when you view as a subset of vertices in the so-called Grassmann graph, its expansion is half. Okay, so we didn't define what the Grassmann graph and what the expansion is, but we'll do it next time. So it's a set of expansion 1/2. In particular, its expansion is strictly bounded away from 1, and that's what is problematic. That this Grassmann graph has sets, in fact, these sets whose expansion is bounded away from from 1. Okay, right. Well, this expansion is really this phenomena that if you are at L, right, which is in this set, and if you move to L prime, you still remain in that same set with probability 1/2. That's exactly what expansion means. Okay. So now let me just say the next couple of lines and we'll end. So this is a counterexample showing that our speculation was incorrect, right? So we cannot come up with a global linear function which has non-trivial consistency with the given table. So can we fix this, right? Can we somehow get around this counterexample? Now here is a proposal. Okay, so what is the case in this counterexample is the following: that the test accepts with probability some constant probability, then there is some point X, okay, and a global linear function G, such that the given table does agree with this global linear function G, which has a good agreement some delta prime, provided we only look at those spaces L which contain that point X. Okay, and this claim is true that for some X, if we only focused on spaces containing that point X, then we can come up with a global linear function with good consistency. Okay, and this is almost like a tautological, right? Because in this example, if I allowed to let's say if I allowed you to pick a point, let's say X1, and only look at those spaces which contain X1, then of course you can come up with the linear function which is F1. That's the function which is used on that set, right? Right, and then of course all these L prime, L double prime, everything will be consistent to that linear function F1, right? So this is a way of getting around this counterexample, right? At least it's a proposal. And the fact that it gets around the counterexample here, it's like a tautology, right? So this fix does work for this counterexample. And this, what I allowed you to do, right? To zoom in to one specific point X and then only look at subspaces which contain that point X. So let's call that operation zoom in, okay? And we are zooming in as we speak. Sorry, back to right. Okay, and then right. So what we'll do next time is there is another family of counterexample which is sort of dual, and you can propose that there is a workaround or getting around that family as well. And there, right, it's for similar reasons it would be called zoom out. So you can propose this zoom in and zoom out as a mechanism to get around these counterexamples, and then make a conjecture that using a combination of zoom in and zoom out, you can always defeat all these counterexamples, and that turns out to be true, right? And that's what is we'll refer to as the Grassmann linearity testing theorem. It appears in the lecture notes, and I recommend taking a look a priori. It will just make things easier in the next lecture. Okay, so let me stop here.
Okay, so thank you a lot. And are there any questions? If not, then
I would have a question.
Okay, sure.
For the first counterexample.
Mm-hmm.
So when you said that there's no global function with agreement for the first counterexample, I didn't understand for the linear subspaces not belonging to to the SI, right? Why this holds?
Yeah, so those which are not in SI,
You take a
just randomly assign something.
Yeah, but say you take any global function,
Mhm.
and then any subspace L. If you assign it randomly, it will agree with the global function with probability 2 to the minus L.
Right. So yeah, so I should have emphasized that for me 2 to the minus L is insignificant. It does not count.
Oh, so L is not constant, but
sorry, I should have emphasized that for me 2 to the minus L is insignificant. What I want is an agreement of delta prime, where delta prime is a constant independent of L.
I see.
Right.
Okay. Thanks.
Good. Yeah, thanks for right.
Any more questions? Okay, if not, then we will meet Subhash tomorrow again for his last lecture. And I think I will see most of you in 20-25 minutes for Shayan's talk.
Okay, bye-bye.
Thank you, Subhash, and bye-bye, everyone.